Hi everybody and welcome to our new video. In this video, we're going to work with the famous children's game named Chutes and Ladders and with one called Not Enojes, but from a mathematical point of view. We will focus mainly on the Markov chains contained in these games, as well as on simulations of this, for which we will use helpful tools like Visual Basic and C++. We will see how the presence of a strategy in Not Enojes creates an interesting generalization of Chutes and Ladders. But first, let's remember that our team is made up by María García, Bertha Lozano, Marisol Romo, and Daniela Schaar. Now, let's begin.
Chutes and Ladders. We don't know if all of you have played this game, so we'll start off by explaining how the game works. First, all the players start off of the board. Then, to settle the order of the turns, all players spin the spinner and whoever gets the highest spin goes first. After that, turns continue counterclockwise. Turns consist of spinning the spinner and moving the player's corresponding token the rolled amount of spaces. If a player lands at the bottom of a ladder or at the top of a chute, then they must travel to the other end of such element. A player finishes the game when they reach the final space, which is the 100th square. To reach the 100th square, a player must spin exactly the number needed to reach the square. If they do not get the exact number, then they have to wait until the next turn to spin again. The dynamic of being able to quickly advance across the board or be returned further back with the Chutes and Ladders makes the game super exciting. As a fun fact, we can see on the board that good deeds leads the player closer to the goal, while mischiefs take them far from it.
The original standard board contains the following sets of Chutes and Ladders. Analyzing this, we can see that this is not a strategic game, and that there is no interaction between players, as players may occupy the same space, so winning is basically a matter of random chance. However, the game is still super interesting and there are many things we can analyze, like how long it takes to finish the game. We can ask ourselves if different versions of the board, like different number of spaces, different placements of Chutes and Ladders, different slide spinners, alter the number of turns it takes to complete the game. To answer these questions, we'll focus on a Monte Carlo simulation and on Markov chains. Before we go to Excel, it is important to say that because players don't interact with each other, as we mentioned before, we'll focus on a single player. As we know from our probability courses and as we have mentioned in other videos in our channel, like Virtual Champions, we can use the weak law of large numbers and observe a phenomenon loads of times in order to see its tendency.
So let's start our simulation for the game Chutes and Ladders. The first thing we do is declare an integer array of 101 entries, where the 0th entry is the starting position. So here we'll declare every entry of the array as the positioning. For example, 47 will read 47. The position 52 will read 52. And then, as we're playing with a traditional Chutes and Ladders board, we declare the entries of the chutes and the ladders. So, for example, if a chute or a ladder begins in a certain space I and leads to the space j, the ith entry of the array will read j. So, for example, the ladder leading from 4 to 14, then the array in the place 4 will read 14. So now we start the game. We set our position in 0, and while the position is less than 100, we calculate a random value between 1 and 6, simulating the die, and we'll add it to our position value. So we already rolled the die once, so our number of rolls will be a counter that adds 1 every time we roll it. So if the position plus the number here in the variable dice is more than 100, then I don't do anything because I want to end the game with exactly 100. Okay? So else if the position plus the dice that I throw, it's different than 0, then my position would be the position in the arrange that declares like the position plus the dice. And this will be repeated the number of simulations that we decide. Here we're doing 1 million simulations. So we're going to print the number of rolls divided by the number of simulations. So basically, by repeating this process a big number of times, we can calculate the average amount of turns it takes to finish the game, empirically. So, running this code 1 million times, we find that the average turns it takes to complete the game is 39.29, as we can see here in the Excel sheets.
As we said before, so far we have played with a standard board configuration with 100 spaces and a 6-slice spinner. So now let's consider the following two alternative boards. They are the ones that are on the screen right now. And let's consider two spinners, a regular 6-slice spinner and 10-slice spinner. Now we want to see which combination of word and spinner is the fastest. That's why let's go back to Excel.
We compute this data on our algorithm. For example, for the 81 board, we have these chutes, these ladders, and we run the algorithm with a spinner 6 and with a spinner size 10. And for the 121, we do the same. We have here the chutes and ladders that we showed before, and we run it with a spinner size 10 and a spinner size 6. So, by running this simulation 1 million times, we get these results. The exact average is obtained with the Markovian approach, and it's here in the fourth column. And in the third column, we have our simulation. As we can see, a smaller board does not always guarantee us a quicker trip, since our 100 squared board is significantly faster than the 81 square board. This suggests that the placement of the chutes and ladders had a greater influence on the length of the game than the actual size of the board. On the other hand, a larger spinner got us moving through the board more quickly, but it has an inconvenience. The larger spinner, the smaller the chance of getting an exact number to finish the game towards the end. Testing the original board game with several different sizes of spinners, we get the following table. We get rid of spinners with only one slice, since we wouldn't be able to skip any chutes or ladders, getting stuck in a never-ending ladder chute cycle and never reaching the final square. We can see that the theoretical expected numbers of turns coincide very nearly to the empirical averages. Analyzing these results, we can see it takes longer to finish a game with a 3-slice spinner than with a 2-slice one. This can be explained since a 2-slice spinner gives us only a 50% chance of missing a chute every time one comes up, while a larger spinner gives us more chance to miss it. Other than that, the average length of a game steadily goes down as the size of the spinner grows, until the 16 slices, where it starts an upward trend. So, according to these simulations, if we want a shorter game, the best spinner is the one with 15 slices, and to have a longer game, we'll use a 3-slice spinner. This game is fairly simple, since it depends entirely on random chance and requires no strategy.
Now we are going to talk about Enojes. This game is a little more elaborate than Chutes and Ladders. Each player has 5 marbles, which start in a lane parallel to each player's side of the board. In order to win, the player must move all of their marbles all the way around the board and back to their side, so that it ends in the finishing lane, which is perpendicular to the starting lane. With the intention of playing correctly, it is necessary that the players follow the next rules and instructions. The order of the players is settled the same way that it was with Chutes and Ladders. Then, in order to exit the starting lane, the player has to roll either a 1 or a 6 in the die. Once the player rolls this 1 or 6, one marble can be placed at the exit space. If a player's own marble is already in this space, then they can take out another marble. Also, if the player has all of their marbles in the starting lane and they don't roll this 1 or 6, then their turn will be over. Once a player rolls a die, they must select the marble and move it the number of spaces indicated by the roll. If a player rolls a 1 or a 6 and has marbles both outside and inside the starting lane, then they have to make a choice. They need to decide whether they want to take out another marble or move one that's already outside of the starting lane. If a player rolls a 6 and decides not to take out a marble from the starting lane, then they will be rewarded with another turn. If they roll 3 consecutive 6s this way, then they must return their furthest along marble back to the starting lane. If during any of these turns the player decides to use one of these rolls to move any other marble outside the starting lane, they will not get another turn. Obviously, when rolling a 6 at the beginning of the game, a marble must be taken out of the starting lane, so the player won't get either another turn. If a marble of one player ends up in the space where another opponent marble already is, then this opponent's marble is returned to their respective starting lane. A player's own marble cannot pass one another. If there are no valid moves, then the turn ends. In order to win and finish the game, as I said before, a player has to move all of their 5 marbles into their finishing lane. Once the marbles are in this lane, then they cannot move backwards, but they can pass one another. The shortcut. This joker or wall space is placed at the center of the board, and it is a strategy a player can use in order to get into the finishing lane faster. It only works during the initial straightaway, which is before the first turn. If the marble may move exactly the amount of spaces needed to land on this center space, then it may occupy this space. The marble may be moved to the opposite side of the finishing lane if the space is not occupied by another of the player's own marbles from this space when the player rolls a 1. This wild space can only be used if it is completely unoccupied by both the opponent's and the player's own marbles.
The biggest differentiator between Chutes and Ladders and Not Enojes is the introduction of a strategy. In this last game, the players still roll a die, which is like the spinner, but they have to make some decisions, so winning is no longer a matter of random chance alone. We must consider that numerous players are acting not only not randomly, but also in a such way that their choices are linked in the sense that their decisions are independent to one another, because the players are free to move their marbles however they want. But the consequences of those actions may have a significant impact on the other players. There are 2 types of strategies: no random strategy, which depends on other players' marbles and decisions, and random strategy, which ignores other players' choices. To be able to give an answer to what will be the best strategy in order to win, we will later on use C++ to simulate a program that can give us those answers. We will consider only 2 players placed on opposite sides of a 4-player board and the following 3 strategies. Aggressive strategy: if a marble can land on another player's marble, the player will do it and send it back to the respective starting lane. If this option is not available, the player is forced to choose a random. Defensive strategy: if another player's marble is 6 or fewer spaces behind it, a die rolls distance away, and the amount of spaces moved will bring the player's marble out of reach of the opponent's marble, the player will choose to move it. If such a move is not possible, the player is forced to make a random decision. And the random strategy: the player chooses a random marble to move. If that marble cannot be moved, another one is chosen at random. We shall remember that the movement cannot skip marbles of the same color, cannot move past the final space, etc. In all strategies, we will also consider that a player will opt to move a new marble out of the starting lane whenever possible. As a second priority before making a marble choice, we consider that a player moves their marble out of the shortcut space whenever possible, given that a new marble cannot be taken out.
Here we have a C++ program with the 3 strategies available. In our simulation, we test each of the 3 strategies against the same 3 strategies, adding up a total of 6 tests. Each time the game is simulated, the player who starts is randomly selected. That is that the program chooses randomly who will roll first so that the game is fair, because there is a slight advantage in going first. We have red starts and blue starts, which tells the number of simulations that have started for each player. However, it is important to mention that the generation of the C++ random number generator is not completely uniform, which may affect the fairness of the simulation. For transparency, in the program, the red player's turn code precedes the blue player's turn code. Then, we ran a million iterations of the simulation. Here are the results. Thanks to the program, we can notice that the aggressive strategy adopted by the blue player is very effective compared to the random strategy of the red player, giving the blue player a double amount of winnings and almost double the amount of captures. Contrasting the random strategy with the defensive one, we get that the defensive is slightly more probable to win, and the amount of times the random strategy captures a defensor is way smaller. Now, comparing the aggressive strategy with the defensive one, we can see that again the aggressive one wins way more, regarding the amount of captures that the aggressive strategy executes. It is still very high, but not as high as it was with the random strategy. After seeing all this, we can say that the pure strategy that wins is the most is the aggressive. In addition, the random strategy is the worst one. So even though the defensive strategy is not always the best, it is still better than the random one and it still has some advantages. Obviously, when actually playing board games, people do not tend to stick to pure strategies, nor do we turn to random choices when our strategy is invalid. Also, we generally play with a mixture of strategies during the game, guiding our choices by the situations we face. Mixing both a defensive and an aggressive strategy might work well. Based on the data, a move that is both aggressive and defensive seems to be very valuable, and the random choices seem to offer better odds. So it is considered a defensive move before defaulting to random choice appears to offer better odds. Regarding the algorithm, we can see that it is not only very long but also a bit complex. As we can see through the lines, the key of this program is on the use of different cycles and conditions. The cycles are used to represent each player's turn, and the conditions help us to apply some of the game rules such as rolling ones or six to take out marbles, the consequences of rolling 3 consecutive 6, and the shortcut space.
In this video, we generally explain and analyze 2 board games, Chutes and Ladders and Not Enojes. We try to focus on analyzing the average length of the games, on the spinner sizes and on favorable strategies that could be implemented. The Visual Basic program for Chutes and Ladders works efficiently and generates quickly a large number of games with any parameters. The Not Enojes C++ simulation was more complicated to implement due to the numerous rules, strategies, and shortcuts that the game has. Making this video, we learned the importance of knowing how the Markov chains work and how we can apply them to real life. So now, thank you for your presence, your attention, and mostly for your patience. See you next time.